We're going to begin our study of simple extensions by first classifying them. And it turns out that there's roughly um, two types of simple extensions. And let me just give you an idea of where they come from with the examples we've done so far. So we've seen extensions like q adjoin root 2 over q and q adjoin I over q. These are simple because you just add in one new number to your previous field to get the extension. Okay? So these are interesting because root 2 actually satisfies the polynomial equation t squared minus 2 equals 0, and this has rational coefficients, so we say over q. And also notice here that I satisfies the equation t squared plus 1 is 0 over q. So that was one type of simple extension we had, and it's going to be, the type of simple extension that we're mostly going to care about is extensions like this. But there is another type. There is extensions like q adjoin pi over q, or c adjoin t over c, or q adjoin e over q. And these are distinctly different in that in each case, pi is a transcendental number, meaning satisfies no equations, no polynomial equations over q. Over q. Similarly, t satisfies certainly no equations over c. Why? Well, c already has the solutions to all of its equations. So it can't, like t is a new thing. It can't be a solution because then it wouldn't be new. It would already be in c. So t also satisfies no polynomial equations. Over c. And then similarly for the last one, e of course is also transcendental, meaning it satisfies no polynomial equations. So this is distinctly different than the previous type of simple extension. So this leads us to a definition. So definition. Suppose K is a subfield of C. And alpha is in C. We say that alpha may not be in K, usually it won't be, but alpha is algebraic over K if there exists a non-zero polynomial with coefficients in K such that P of alpha is 0. So what this is saying is that alpha satisfies some polynomial equation with coefficients in whatever field you're starting with. Usually we'll start with Q, but not always. Otherwise, let me underline this. Otherwise, alpha is called transcendental. It transcends algebra. Transcendental. I can't spell. Dental. All right. So if we go back up to our introductory example here, these are algebraic over Q. That's another way of saying this. So root 2 and I are algebraic. And when Q is the base field, we just say algebraic. So we don't have to say over Q. It's only when we've changed the base field to something else that we'll say algebraic over whatever the other thing is. And pi, t, and e are all transcendental over Q. And again, like with the Q, pi and e are transcendental. Let me back up here. Transcendental. And again, over Q is assumed when you say that. But for example, the C adjoin T over C, that's not over Q, that's over C. So let me just be clear with the language here. T is transcendental over C. All right. What I just said is kind of conflicting because I required that the alpha be in B and C, but in general, this is still considered a transcendental extension. Okay, all right, so these are roughly the two types of complex numbers. I mean, by roughly, I mean like this is a rough categorization of the two types of complex numbers that we can add to a field, the algebraic ones and the non-algebraic ones. Let's look at maybe, let's see. Let's look at a couple more examples real quick, some kind of non-trivial examples. So I really want to, in this, emphasize the sort of over k part. So we know, for example, that pi is transcendental. This is a tedious proof that is in one of the later chapters of the book, requires some analysis. We're not going to go over it in this class, but I encourage you to look at it. And when you say transcendental, you mean really over Q. So I'll write it one more time. However, pi is, also the same is true for the square root of pi, certainly. Because if the square root of pi would be algebraic, you could cook up a polynomial that pi would satisfy. But notice that the square root of pi is algebraic over a different field, over this field, Q adjoin pi. Why? Well, it satisfies the polynomial equation t squared minus pi is 0. Pi is an element of Q adjoin pi. So it satisfies this equation, so it's algebraic over it. All right, so just be careful with this word over. If you don't use the word over, it's assumed Q. If you do, what was algebraic or transcendental over Q, it might change, right? These things might change. And this requires a little bit more of an argument, but I welcome you to read the book where the argument's given.